Wait a second. I can probably click on the same thing.
We're live now, Venki, I guess. Milton?
Give me a second. Okay. Hello, everybody. Thank you very much for one more time, everybody here to see everybody here one more time, Mr. Marcello, and I am very proud to present the latest lecture about artificial intelligence. And our distinguished guest, Marcello Benati, and Venk, your colleague from the same company. And Marcello, feel free to teach us about the importance of mathematics for AI. Thank you very much.
Absolutely, Milton, and the whole team at University of São Paulo, IEEE. I'm very grateful for this opportunity. I have my partner and one of my mentors, Ramartha Venkata-san, also known as Venki, is one of the world's leading mathematicians, cryptologists, and works at our engineering group for AI. First of all, in the first two editions, we talked primarily about the importance of ethics in AI, because it's important to get the right frame of mind for having ethical things. Then we talk about some of the principles in AI, how we use them on a day-to-day basis. But today, I'm going to really jump into the two areas which are the deepest importance. And for that, I like to always come in and take two quotes. One of my favorites is from Galilei Galilei, which is the mathematics is the language in which God has written the universe. And whichever God you represent, that is the way of representation. And then a lot of people ask me when they work, computers can do everything. How can I work with everything if I don't know math? So I basically say, hey, mathematics is the principle on which everything that builds around machine learning, around artificial intelligence is built on. And the computers are not going to make it easy. You have to have this fundamental of mathematics built into to understand and to work with computers and to make sure that things work well. So today we talk about artificial intelligence as not just a machine standpoint, but we mix a combination of human capabilities and we enhance them, we augment it. So sometimes we talk about augmented intelligence and how you bring those things to bear, which incorporate the analysis, the vision, the prediction, the language combination, the perception of the world, reason and interaction. All those things are represented mathematically. And in order to make things easier for people to understand, they have to have a very good, solid foundation for mathematics and how things work. This is what's happening as we talk about the digital economy. And this is a viable situation across every single technology and artificial intelligence company. We start with data, with information that you're trying to bring in somehow. That data has to have people have to have an understanding of how that data works, and then they represent them mathematically to algorithms. An algorithm is basically a set of instructions on how to get things to get done in a term or set of instructions for the computer. And majority of those algorithms are written in a mathematical language that can evolve. Venki, feel free to jump in whenever you want to add on to this one, because right now I'm just going to overall on this one. So things that I always say that are very important are a few categories. For you to come in effectively working on artificial intelligence, on machine learning, you have to have a very strong foundation on some of the basic mathematical principles which are important. I'm not going to discuss each one of those elements individually. I'm not going to have Venki talk about those elements individually. But I think the importance, as you guys becoming more versed in artificial intelligence, in machine learning, and those characteristics, those are the areas that you need to highlight, areas that you need to develop in order to have a sustainable machine learning and AI career. And I find in a career for this past 20 years that people, for quants and some different ones, people that do not have a strong mathematical baseline or understanding do not understand the harder concepts. So with that being said, I'm going to go a little bit and talk a little bit about some of the principles that we find important. The first vector is a good, solid understanding of linear algebra and how things work. AI machine learning works very, very based on vectors, on scalars, on how scalar multiplication, inner product or dot product, vector projection, and things of that particular nature. Second one is matrices. How do matrices functions and how do they evolve working from each other? And those mathematical functions are quite important. Venki, do you have any points to make about vectors and matrices that are the importance of those? You're on mute. Venki, you're on mute. Sorry. We're working with a different program on the outside, so I still see you on be mute. So whenever you work with those, with the ability to work with algebra and those different systems, those vectors and matrices are keys to understanding how every single function that you are going to define on a machine learning model, on an algorithm, works. And that importance of how to work on this multiplication with scalar multiplication, with what we call Montgomery multiplication and division, is key for elements such as encryption, cryptological enforcement of data, and some of the information where you take large prime numbers, multiply them together. So as an artificial intelligence engineer, as a machine learning scientist, we always look at those numbers and very strong area on those particular areas of knowledge. Matrices, in terms of how do you understand how matrices function and how do you do transformation, how do you do identify different groups, are very, very important from the standpoint of how to evolve the algebraic equations. And then when we look at search engines and how categorizations are functioning, for example, in terms of Google or Bing or any of the large search engines, we have what's called eigenvectors and eigenvalues, in which they have the ability to bring concepts to mathematical practice, and they bring them together and they showcase how those numbers are functioning. The other element that is very, very important from the algebraic standpoint is the principle of component analysis, understanding what the functions are within each one of those components, and then apply this concepts property as an application of those particular algebraic concepts to the application or to the algorithm that you're trying to develop. When we come into value decomposition, with single value decomposition, that it teaches you, which is again baseline in algebraic formulas, that it comes into statistics and some of the other functions within mathematics that enable you to take those decomposition methods and apply them on an algorithm. The function of algebra primarily, when we work on the situation, is to verbalize the algorithm in a language that can be easily understood across development platforms. So if you use algebraic methods according to vectors, matrices, and this different vectors utilization and a format that is understood, you can develop a program that can be used by folks in Brazil, folks in Europe, folks in India, China, different ones, because the language of math is universal. There's different uses or interpretations of how to basically go to those things, but it's a fairly universal language and fairly can be understood. The second point that we always should come in there, and so come into matrix theory, and I'm going to bring into, hi, Venki, sorry about that.
It kicked me out, so I'm back.
Okay, no problem. So we were talking about the importance of linear algebra to the practitioners of machine learning and AI.
Yeah, okay. And I can tell something about it. So it can be said that the only thing that all human beings can do, things which are linear algebra is the foundation for all of that, almost everything. And even when things are non-linear, they'll try to make an approximation with linear model and do it. And what is very interesting about machine learning and linear algebra is that, first of all, it is always on very gigantic dimensions. the matrices are so huge, it's unbelievable. And and somehow you solve a linear algebra problem and actually means something in practice as to how to make a guess as to what's the most likely outcome and all kind of things. So the people have invested a huge amount of money in learning, they're taking the theory and doing things with it, and fast and efficient, all the kind of things. Even the most complicated networks, deep neural networks, they're not just really linear, but they're essentially made up of linear components. So you might have heard about, there are lots of complicated things like manifolds, groups, all those kind of things, but still they'll have something linear, like a Lie algebra, something to pose everything in linear form and solve it. So basically, all human beings know how to solve these linear things. And in the machine learning things, it got to be huge, and you solve many, many different type of problems. For example, if you want to go to a restaurant and everybody's talking to each other in different table, and you want to, somebody's playing a piano, if you want to hone on to some particular conversation, you have the entire din and bustle going all over the place. And if you want to go and get the conversation in the remote corner, you can do what is called principal component analysis that is written there and listen to only that, actually. So this is very, very interesting as to what other things you can do. And the linear algebra is just entirely limitless. Yes, the things like eigenvalue, eigenvectors, principal component analysis, singular value decomposition, this is called the spectral analysis. It's like if you have a signal when you speak, you have an audio signal and it has frequencies. It's a matrix is like a speech, but all the eigenvalues, eigenvectors, principal component, they're like frequencies. So these are these are extremely powerful. And last but not the least, the power of linear algebra. If somebody wanted to make this universe so that linear algebra can succeed, I think. For example, if you take your own picture and think of it as a matrix and you do a singular value decomposition, so your picture may be 4,000 by 2,000, whatever, right? But it can have potentially 4,000 singular values. But after 10 singular values, there's nothing left. So basically, you can decompose all these things. And why this happens, we do not know. They're all like that. Even if you have audio, if you we can only listen to up to 20,000 hertz. So people can, it's enough to filter them up to that point. But other things we don't know. In the audio, video signal similarly. So somehow the low frequency components are the most important. This is true for even matrices. And it's very interesting to note that audio, video, matrix data, they are all the same properties, essentially, if you think about spectrum. Thank you. Make sense?
Yeah, that makes a lot of sense, Vicky. Thank you very much. The expectation, when we talk about AI, most of the work that we use in all the GTP and Turing and some of the things are based on the linear algebra and some of the principles that we talked about in here too. I went a little bit on the matrix theory about understanding how things work in terms of on the matrix theory, the computational structures and neural systems, because a lot of people use the computers and the matrix theory for what we call the input layers, the hidden layers, which things the mathematics hides behind them, and then the output layer. And then they're beginning to use what's concept of what we call the neural networks. And to do this, we have to compare the neuron in a human brain to what we call an artificial neuron. And that theory took about 20 years to have an input synapse, which is an input coming into the process. Then we have the middle layer, where it's actually the composition or the entire mathematical process that's taking place, and then an action or functional activation that takes place on the output side of it. The mathematical functions happens as a vector of data comes in, whatever that data is, whether it's a signal, whether it's a human thought, or a number, an integer, or a voice, or anything. Then the artificial neuron takes and receives that information, processes it, and processes an output on the outside part of things. One of the things that always people talk about is what we call the page rank, and how the math works within Google, Yahoo, and some of the different ones. Larry Page, I took the algorithm. I have an entire document that explains how the algorithm works for the engineering students into detail. I'll put it into the particular area. But when we look at hypertextual search engines, like categorizations or anatomy or those things, the application is very, they're using eigenvectors and using this known vectors that have been known for millions of years, and understanding how people calculate those particular scenarios. So typically, remember the concept we talk about neurons as an input. So there's large web pages, that's input set. And then the index and catalog is the process that's happening. That's basically invisible set, not known, but it's a computation. And then they do the rank value. And they calculate the value of P is this, where being this formulaic approach. It brings down the formula where all the pages are aggregated, categorized, and put it on that one, and put it as a subset into the matrix in those particular terms. Not going to go into details. I will send. I'll make sure I'll put into the group a PDF that explains how the calculations work and how they function. The second part is actually very important when we talk about. We have the linear algebra, but the second part that's very important to AI is what we call the calculus aspect. And when we talk about calculus as engineering students, you guys always got to remember, and people in colleges and advanced have to have a very strong foundation and understanding how calculus functions, so they can understand functions, how do they do scalar derivatives, and then understand what gradients and the properties of the derivatives are, to bring together vector and matrix calculus. And remember, again, we met vectors in matrices in algebra. As they evolve into calculus, you get to different higher level, and start bringing them together to what we call scalar functions, and the combinations of those functions together, bringing what we call the Jacobian or the four combinations. Then the last one we like to talk to that's important and imperative when we find, and by no means, and those are the only functions that exist within mathematical functions within AI, but is what we call the gradient algorithms. And we have an understanding of what the local versus a global scale versus maximum and minimum values or subsets within the calculus algorithm is. And then we have the functions, the saddle point, the convex functions where things get together, the gradient descent algorithms where things are categorized to a certain degree and the data is sorted and brought together to a certain level, brought into different batch, and different performance that occurs. Depending on the type of algorithm that you're trying to use for machine learning, for different type of things, you will use one of these functions for a specific reason. If you're trying to do a sort, there's hundreds of different types of sorts available. You're going to use the one that's more effective to the type of data set that you're trying to use to become more efficient on the outside of that one. Thank you. Any feedback on that one? You still mute. For some reason, you got muted.
The way to think about the value of calculus is to imagine yourself in a very wide open area, but it's surrounded by mountains all over. Okay, and the path curves up and down, and there is a point in which it rises up in two directions, left and right, and it goes down. Path goes down and the forward and backward. That one is called saddle point. But you don't know which way to go, because if you want to go up or down, depending on what it will take. And there could be also in this area some holes which go too deep in the ground and 2 feet deep in the ground, and there's a hole in there. You come out of it, and somewhere there may be 100 feet down hole on the terrain. And then maybe a peak which has got 1,000 feet up in the sky. The optimization algorithms, gradient descent algorithms, is to use some method by which, if you want, you can get one of the peaks, top peaks, or you can go to the bottommost hole. But the real fear is that you may get into a hole which is locally minimum, and you might not be able to get out of it. And the saddle point will be completely confusing. But the point is that the gradient descent algorithm, you should think about it as a way in which, hey, I'm going to go the way in which is the steepest going down. And mathematical calculus will tell you how to find the direction in which you have to go. And the the gradient descent algorithms are really impressive. They were invented in the 70s and the 80s and things like that. But what happened afterwards is that gradient descent. What happened is that people figured out what is called stochastic gradient descent. Stochastic gradient descent is something. What it does is that suppose you want to optimize some function, and you have given a matrix for it to specify what you are optimized. And what you do is that they found out, instead of taking all the maybe billion rows, if you take all the rows, you'll get indigestion. The computer cannot have it. So you have to do it one at a time, but you'll get the same result as you have forgot the whole thing. That is the origin of stochastic gradient descent, and it's used by everybody. What I really encourage for you to do is to look for a professor in Stanford who has a video about how to use gradient descent for teaching a car as to how to drive. And what is interesting about the video is that, I'll try to find it now and put it in the link, is that the car is just learning for the first time to drive on the road, and it's his job. There's actual real cars going. There are intersections, and it's learning all the things. Okay, so that shows you the power of gradient descent. But however, if you want to make all the supposing you come to Sao Paulo, which is pretty much like driving in India, if you have cars which are doing AI to find the way to drive, and at the same time Marcello's brother is driving, Fabio, it's a kind of difficult because the modeling is difficult. Fabio is Marcello's brother. When I was in Sao Paulo, he drove so fast, I got really scared actually. So he just makes huge turns and goes. So the human beings and automobiles coexisting will actually have challenges for gradient descent algorithms and teaching how to learn. However, if you want to sell, $200,000 worth of beer from one place to another place, load it in a truck, and it goes straight for 2 hours and get off the exit, those things are really neatly done already. However, the real challenge is this also exposes to you what machine learning is. The real challenge is, if you use it in simple cases, you may get very far, but you want to coexist with human beings and do something, even when you don't have the proper model, it's highly challenging. And this area is, if anybody wants to get lots of challenges, you should do it. And there are people who believe that all the cars will be driving automatically. They have to go to Sao Paulo or India, then they'll figure out what's wrong with the idea. But it's an exciting area. All the things that the slide are very important, especially the last two lines. Thank you.
Yeah. The stochastic one is an interesting one. And the example of Sao Paulo driving and India driving is very interesting, because the machines themselves are, if we have all the cars on the road run by computers and respecting the laws and the rules, then it's the likelihood of something working well is going to be good. But the second we introduce an element that is unknown, that was not calculated, then you're going to have a problem. So the behavior of the drivers, or an animal that jumps into that one. And we see this in AI models for cognitive, the learning models for automated vehicles and some of the different ones. And we're far off yet, because sometimes they can be confused. One of the problems we had with Tesla, for example, it saw a white reflection on something and it confused it. It overreacted and it hit a truck because it thought it was a clear space. So the cameras did not distinguish properly, made a decision, and the decision was wrong, causing an accident. So remember that the importance of those things. I will, Venki send me the document later. We'll put it onto the group. So it's very important for the standpoint of use. The first part of this presentation, we're going to talk about this principles. Then I'm going to open up the room for conversations that we have with some of the folks, the participants, with Milton and Walter coming on that one. One part that I find very important is the part of the Trinity is the ability to learn for AI, machine learning specifically, is statistics and probability. A lot of the biggest challenges that occur when you find in machine learning, but with some Python and R languages, mathematical modeling languages, are statistically related. They're calculating probabilities. So you have to have very strong basis. If you're doing predictive modeling, if you're doing mathematical or quantic predictive modeling, you have to have a very solid statistic model. I pulled back a document that I had that we used to do to test quants that we're applying when we were working on a mathematical company, or they're doing a quantitative prediction for stock market. And I pulled back one of the test we used to give them, and the different ones. I'll share with Milton to share with somebody else. Take the test to see if you will pass. It's kind of funny because unless you're trained in those basics of calculus and statistics, people will not understand how that works. So with statistics, you got to remember the frequencies, the amount, the type of approach, the dependence, or the things are not independent. Most people that we work with data, and Venki and I work with a lot of people that work with database, work with people at Microsoft, they always want the data to be nice, clean, and what we call normalized. The normalization of data brings clarity to the mess. But here's the problem. The beauty of data is on the outliers. So if you want to predict something or predict behaviors, predict understanding, all the factors are on the outliers. Coming back to the previous example of a self-driving car, if you have all the cars in a system that's a closed system, and you have full control of the system of all the cars and all the components, then it's kind of okay. The system should work normally. That's a closed loop system. However, the probability that somebody's going to make a change, that a human is going to jump in a car, or a dog is going to cross the road, or some things, those are the areas that statistics and probability are going to jump into. So if you're in Sao Paulo in India, the probability of somebody driving erratically, it's extremely high, and we have to bring up that one. Oh, there it goes. Thank you. Put out the links for the specific ones there. Other thing is random variables. We called about the variance and the distribution of those joints and conditional variables in terms of probability. Very, very important to have in there. And when we're working with a machine learning at Microsoft, we began, and Venki can talk about this one, about how to apply those expectations, the variance, and then the distributions, and test. Remember, machine learning is an iterative process. You create something, you make an assumption, you validate it, you test, you check the probability, then you check, hey, was it correct? A and B test. When you do website, hey, what people are using this ones. We feel that people using a light font and a black background is going to be better than a black font with a black background, or a white font on a white background. We know this because we test this probabilities on that standpoint. So the other one's what we call the Bayes theorem with MAP and MLE, and very important for statistics and probability. And unfortunately, in the scientific world, as we know, and you guys know that from the engineering, is the minimum statistic value, the possibility, the probability of something being there. A lot of the things are coming up to this medium baselines. Hey, the statistically significant medium is what becomes the most important. So statistically significant has become, it's a good way to measure things, but usually people stop there because that's where they get the grants and grades and some different things. So you got to go beyond that. You got to understand the statistically significant, but understand the causation. And that's important with regards to machine learning and as well as AI. If you just stop there, things go stagnant, and they'll probably come down pretty strong. The other is what we call distributions. How do you distribute things from the standpoint of data, information, visualization? And those are the binomial, Bernoulli, Poisson, exponential, Gaussian methods. And how do you search, how do you categorize, and how you bring the data coming to that one? And then you remember that one, the conjugation of priors from that standpoint. So probability, statistic, calculus, and linear algebra are extremely important combinations going together to give you some of the different subsets. I always say the must-haves when we talk about statistics is, you have to understand what those terms mean and what they basically represent. I'm not going to go to each one of those. The purpose of this today is not that one. But you also have to check the validity of those beliefs. So the maximum, the MLE, the parameters, how the estimations work, you need to have those concepts functioning very well from that standpoint.
Okay. I can offer some comments here. Go back.
Becky, sorry.
So the thing is that probability theory was supposed to be magic in 1800s until in 1933, A. N. Kolmogorov, one of the greatest mathematicians in the century, actually made it very mathematical. And after that, everything took off, actually. He's also the foundation for probability as well, many mathematical sciences. He's also my academic grandfather. But the point is that why do we use probability theory? That's actually how to remember, because you don't know what exactly is going to happen. Exactly, but overall you'll know what happened. So now imagine in Sao Paulo, everybody wakes up in the morning, gets up in the go to the kitchen, brush their teeth. Some of us brush our teeth, some of us don't. Have a tea, coffee. Somebody may have whiskey. Who knows? All these people, some may be sick, some may be going to work, some may be cooking, whatever. But what you need to do is to imagine yourself observing 5 big traffic junctions. Okay, and the number of cars that go through it, the number of people walk through it, number of people on all the four big junctions will more or less have the same patterns. Even though every single neighborhood, people getting up, waking, walking the road, they will have different probability distributions of people coming in. The amazing thing, it was invented. It's called the central limit theorem. What it says is that if you start observing things on a very large data sample, they will have essentially the same features. Actually, it's called the central limit theorem. It's one of the reasons why probability theory is usable even when you don't know the exact distribution. Like Marcello was saying, you have to check your assumption, but it's also possible to design your algorithms in such a way that what is true for most distributions will actually make your ideas robust. And since we don't know everything about everything, and it's for example, even predicting the traffic at a one singular big junction inside Sao Paulo or Chennai or even England, right? Everybody's supposed to be more regularized. It's impossible. What they can show is that the number of cars going through this junction on this road from in this direction will be on the average, you can say a number 50 per 30 seconds, and it can vary between 50 and 70 on the upside and 40 on the downside. These kind of patterns you can reliably do. So what the machine learning does is that tries to figure out most likely outcomes without, even though you don't know the exact distributions. Marcello has listed binomial, Poisson, Bernoulli, Gaussian, exponential. So exponential is what you get when you start watching people arrive at a particular point in a queue. So all these things are very different things, but they all have the same property that if you watch long enough, you will actually be able to predict everything almost clearly. So what machine learning models must use probabilities because we don't know everything. And you want to do it in such a way that, for example, Marcello was saying, you have to validate your assumption is correct, Poisson or Bernoulli, but it may not be the case. But so what you do is that you design an algorithm which will work for all of them. Typically, it's possible. Thank you.
Yeah, and in fact, let's stay on for a little bit. When we do it, typically, once you look from a framework, from a mathematical standpoint, you have assumptions, and you must validate those different things. We work on the day-to-day basis across the different products we have across Microsoft. That is constantly, if we decide, for example, to put a feature in Excel, for example, a feature in Excel, we make an assumption that people are likely to use it. We have to measure. If, for example, hey, we're going to put in quadratic, we're going to open Excel with a quadratic equation, a resolution of a quadratic equation. That's a bad assumption because we don't understand. Only people are interested in that. Most people use Excel for different functions. So if you test it and people don't start using Excel, that's a bad thing for the business. So from an AI standpoint, from a product decision, there has to be certain tests. So what you do in a scenario like this, you say, hey, I'm going to go into students in high school that are learning calculus or algebra and say, would you like to have an add-in for a quadratic equation? And you test for those students to see how that becomes on the day-to-day basis. So all these functions are from the machine learning and algorithmic perspective, they have to be tested. And we apply on a daily basis where we do testing of our products and services and the adoption of the products and services with the real data from the standpoint. As when I spoke about ethical AI before, it's an interesting situation because we can only have the telemetry. So for example, if I have Venki using Excel to do a calculation or something, and his Excel breaks, I do not know what Venki was using the calculation. I know he was using Excel. I know he was using a 64-bit calculation of in Excel, and I know the parameters of the machine he was using during that particular computation. But I do not understand the content that he was doing it directly. So the idea for me is to prevent Excel from breaking when a likely scenario situation has that. That is what we call the normal understanding of the testing of machine learning and testing the models to validate that and receiving the telemetry to see. Then that's Venki's machine. Then the second thing I need to just check is, number one, how many people are trying, and I don't know that Venki's Excel was Venki's Excel, because I have no attribution to know that it was particularly his user machine or whose username it was. However, if I want to take a function or pass it across 10,000 people or 100,000 people or 1 million users or a billion users like you have in Excel, you're going to test to see how many of those are doing similar type of calculations. And that's how we call it prioritization of features. So my assumption in the world is not going to be 1 million people doing calculations in Excel, such as the one that Venki might be trying to do, unless they're students in university or in academia. However, if we see that those are big trends, those are features that get prioritized and develop much more on the different subsets. That is how computer companies, this is how research companies decide on how features are divided and how they use based on the data and input that's coming in for the telemetry of systems that are happening within those systems within the company. That's what we do at Microsoft for understanding. Some of our competitors have a lot more data about what you are doing and how the data is informing, and then they calculate what we call, coming back to the principles of what we call digital twins, where you effectively have a combination with all your attributes of data about a specific individual, about a specific social media user. And then those values, each one of those attributes has a whole subset of algorithms associated to it. So for example, if I want to validate, calculate your political opinions, I'll send a survey to see if you lean left, right, or middle of the way. And then I send a follow-up to see where it goes. And then I start pushing content based on that information. And that's the machine learning, that's the predictive model. All those functions there are in place, working to present you information. And then validation. So if you click on content that I send you that's either political left or right, and you click and you start liking those, then my valuation, the algorithm is being evaluated, and the digital twin is say, hey, we have a persona here. They like this kind of things. They like, they like to drive in Sao Paulo, and they brush their teeth. Well, we know that that's a persona type of scenario. So what can we sell them? Well, we can sell them information on toothpastes, toothbrushes, and coffee versus tea. That's the kind of information that machine learning algorithms use to calculate and refine the models that are related to each one of the different models here. The other part that's actually very important, we said there was a trinity, but there's actually 4 different things, is the understanding for machine learning and to AI is what called the understanding of information theory. And the way I like to bring this combination of information theory is the combination or the amalgamation, what we call calculus, statistics, and probability brought together. So if you bring something, the entropy is how do you measure uncertainty in an environment? Like Venki was talking about the self-driving vehicles. Well, that's a principle, a Shannon entropy. There is a principle that has to, if it is a closed circuit loop, that's fine. But what if somebody breaks the closed circuit? When that's a principle called entropy. Cross entropy, which compares the probability distribution, tells how similar they are. Again, the concept that we talk about, the digital twins of people, 2 different people. Let's take somebody from Sao Paulo and India and the way that they drive. There's a lot of similar type of things. But in Sao Paulo, if there's a traffic jam or accident, they're going to stop. In India, different parts of the world, if there's a cow in the middle of the road, it becomes a circle. Different types of principle, and there's cross entropy that exists between those different particular groups. And then we have some of the subsets, the divergences, on how similar the 2 probability distributions are. So information theory brings all those elements together, and it's very important for you to have that on that. And then you have what we call the Viterbi algorithm. that is used in natural language processing and algorithms. It has to do with inference, language, voice, pitch, translation versus a known set of data and versus interpretation. A lot of people understand and learn when machine learning was beginning to be translated in the 80s. They have the example of the Chevy Nova. For the United States, Nova means new and evolving. But in Spanish and Portuguese, Nova means it doesn't go. They didn't have the inference. They didn't have the natural language processing to understand that Nova in the Spanish language meant does not go. And therefore, it created a problem with a particular scenario. And last but not least, again, is the encoder decoder when you use machine translations and real neural networks and some of the other models where you have to understand how information is coming in there, where it's coming on the encoding and decoding, and what the frequency of that information is to put it in validation and standpoint of that one. Thank you for putting out the Cloud-Shannon entropy subset. So with that being said, these are the basic ones. I have some links in terms of the divergences, the mutual information, the Markov chains, and then the stationality. But we put in some links on the back of this conversation of some of the tools. There's a very interesting workout on the IEEE. The link is in there on that particular scenario. What we like to do right now in this last 10 minutes is open it up for questions and discussions or any topics that you like to talk about with regard to machine learning AI. You have Venki and myself open, and feel free to come on mute, and Milton and some of the folks open it up so we can have it an open discussion with the folks out there. Milton?
Okay. First, thank you very much, Marcello, Venk. I appreciate a lot your explanation. And I like it, the good expression you use it to information theory, amalgamation. Very interesting, because normally when I study AI, there are a lot of conception that you have to use, as you and Venk said. But this expression, I thought it's a excellency word to resume the important theme, to briefing about the almost everything you said. Give me a second. I'm checking if we have some question at the moment. Anyone? No one. But I have one question, Marcello. When you said about the calculus, and I have the feeling that when we approach a problem to solve, sometimes our mindset remember the calculus tools, for example, differential equation, integral, etc. But the algebra, as you said in the first, is very important to fix complex issues. No? As Venk said about the restaurant, that you have to use matrix to design the issue, to make a good approach to fix. But nowadays there are complex systems area in science, and many tools as you use it to try to solve any issue. For example, cellular automata, sorry. Something like fractal, etc. I'd like to know if you and Venk has some more suggestion to use this kind of tools from complex systems.
Let me pick up cellular automata. Right.
Okay.
Cellular automata is think about a n by n grid, right? And yeah, everybody is standing in one of the corners, like it's a n by n grid, like every coordinate, the n squared people standing on it, right? And The way cellular automata works is that everybody looks to the right, left, diagonal across, and look. Everybody has a number. Looking at the numbers, you make a suggestion as to what to do right now, right? This looks like a very stupid thing to do, but the point is that it's capable of doing everything you can imaginable. You can prove it actually mathematically. And the Conway has a game of life. You should look for it. Game of life. It's basically based on it. And there's a book by Wolfram about all this kind of things. You can go look at it too. Now, if you want to use cellular automata for machine learning and all this kind of things, that you're going to have difficulties because you don't know how to frame it. Okay. So cellular automata are good for explaining what happens in a material that there's lots of think of it as lots of atoms as magnets and how they align kind of thing. You can actually write nice ideas for them. But the way in which AI works is it's far more geometrical. It's like it happens in much higher dimensions, and cellular automata can only look particular cellular automata out behavior can be depend only on its neighbors. But a typical machine learning algorithm, when it makes changes, it depends across a very large very large vector and things like that. So because of this, cellular automata, while I really like it, it's not used in machine learning as much as should. That you should. Part number one. When you talk about what is the other thing you said? Cellular automata. One more thing you asked. What is it?
I said that fractal, for example.
Fractals. Yeah. So fractals are amazing things. There's lots of books because everything in the world is supposed to be fractal. What that means is that we know about one dimensions, x-axis. We know about two dimensions in two planes. Fractals are those whose dimensions are actually a fraction between 1 and 2, or 2 and 3, and 3 and 4, things like that, right? So how do you measure the dimensions? So you have to write the mathematical formula to figure out. For example, if you take internet traffic, right, and arrival patterns, all the delay, all the things they can be modeled by a fractal. And you can actually, there are algorithms you can use to figure out the fractal parameters of those. That is because it's a quantity between one dimension and two dimensions. It could be between 2 and 3, but not much more. But it is true that in almost everything in nature has a self-similar pattern. So let me just tell you about the internet traffic. So suppose in your organization today, you find out the traffic in the morning up to evening. You plot something like whatever you want to plot. But then you do between 6 o'clock to 12 p.m., 6 a.m. to 12 p.m. And then you plot it between 6 a.m. and 9 a.m., 6 a.m. and 7 a.m., 6 a.m. and 6:30, 6:15:30. You plot it under general circumstances. I give you the plot. You can't tell which one I drew with. I drew all these plots. You can't tell. There are meaning that by zooming in more and more, you won't get any more details than what's in the top. The self-similarity is a pattern of nature. It's amazingly worthwhile thing to study. And Mandelbrot made all kind of models for it. You can look for them. But as algorithmic, so the only place I know fractals are important is to understand estimate the fractal dimension of some traffic patterns. Otherwise, they're not used in machine learning and all these things because there are no natural analogs of that in quantities are arising in machine learning so far, and at a big scale. So it won't go into the must-haves that Marcello put down. You have to learn the various algorithms that are in the list, and then you can make some impact. But however, what you need to understand what you really need to understand deep neural networks. It doesn't come into any of these things. It's kind of a thing on its own. And they were new in 70s, but not in 70s, but in 90s, because of the large computer availability and a lot of data, things worked out. For example, if I take a picture and I want to produce a vector of numbers, right, such that I took the same thing of Marcello, that should be far off. On the other hand, you're shaking your head between 2-3 seconds, 1 second delay, I take a picture, it should be closer to it. But my vector should be only like 100 and let's say 256 bits. The picture is very long. I are allowed only, you can do it. It's called perceptual hashing and all these kind of things. The important thing is that these sort of things are very technical things to do. But after neural networks came, after Professor Hinton's work, he's a professor in University of Toronto, came all these kind of things. Audio, video signals became terribly easy with the deep neural networks. And so basically that's a norm. They're very, very difficult to displace, and definitely the fractal notion is extremely. If you come to my house, there are like half a dozen books on fractals, pure hardcore math books. I like them, but they're not really the mainstay of a machine learning algorithm. They're very important to understand, but traffic analysis maybe, yeah.
Yeah, and fractals, and we take Mandelbrot series and Julia series to understand the patterns of growth. And we calculated those, for example, with COVID progression and explosion based on distributions of COVID by seeing the patterns of people going across. So fractals are very important subset. And Milton, most people will approach machine learning from a mindset of where they're stronger. If you're very strong in linear algebra, probably those are the methods you're going to approach. If you're very strong in statistical modeling with R, that's probably going to try to address those. It's very important not to have the bias of only using those tools. If you're very strong in a statistic and you know R and you know MATLAB, if you know Automata, then use those tools. If you are not strong, find yourself to challenge some areas which you're not, like learn Python, some notebooks, to understand how those things are expand and cross-pollinate the problems that we find. When you start looking at some of the different ones, you're going to find that in machine learning and AI, a lot of research companies worldwide are working together. GTP3, Turing models, some of the different ones are coming in, are unifying and working together to beat some of those parameters. And each worker is developing and building on the top of the other ones on different groups. So learn those, take those tools. Those are some of the basics that we talk about, what is necessary when we talk about math and AI. I was thinking when I was putting this together, and I didn't have a chance. I just spoke to Venki today about it. So do I take an algorithm for like a image decomposition, and do I break the algorithm down mathematically to explain how we go about it? But I thought we could do that sometimes in the future to see how things evolve. From the standpoint of GPT-3 and image calculation, that's about there is a GPT, the DALI and DALI 3, where you can take verbiage, natural language processing, and create images based on that one. And the ability of GPT-3 is so strong and doing so well that you can say, hey, I want a picture of 3 people talking on a computer in modern style or Picasso style. And the quality of the rendering is going to be absolutely incredible. However, that takes a lot of compute and processing power, which costs money. So that's the situation. And the AI is the compute and cost models there. That's the balance that we come onto that subset.
I got it.
Thank you, still muted.
Venk?
Oh, yeah,
you
here we
said
go.
something? Oh, okay. I got it. Yes, normally it's very hard to hear people like you, and sometimes I want to use any time to ask the simple and the complex questions, because it's very hard to have guys like you.
We had a very good question in here. A lot of people, this man, consolidated for me. We know all those basics have been there for dozens of years, but because AI now is the sexy thing, people are now beginning to jump into that and understand what are the basics coming in there. We have in the code hub, I was just playing with a GitHub code where you verbally explain to something. It's called Copilot. If you go into GitHub, you can, I was fascinated. I was just doing all these little programs right before this. I almost missed the whole thing. Recent books, recent printouts of things are very, very important because people want to know how to jump in and to capitalize and learn this. It's good to have this interest in that. All the knowledge that exists for machine learning, algebra, calculus, and communication theory exists for a long time. Bringing them together is the way that people are doing well. People that are working, I think the next generation of machine learning, of different things, are the people that are learning those skill sets, are coming to the marketplace and evolving those pretty well. So that's a good question there from Induscom.
Yes.
Yeah. It's,
Yes.
I mean, I think the growth pattern is going to be there, significantly growing extensively. And Milton, and by the way, for University of Venki, hands up, you're mute.
That's an important question. Let's go back to a much simpler question, right? You have a movie which runs for 2 hours and so many number of bits, right? When they first came out, it was in the audio videotape, and then it was in a laser disc, and then it's in Shawnee, and then there's a DVD. Now it's a Blu-ray disc. It's remarkably accurate. And while we use mathematically inspired techniques to achieve it, there is no explanation why it should have succeeded, so that you can have a shiny little disc which can play the James Bond movie with such an accuracy. The beauty about the whole thing is that we use mathematical models to let us think about what is there, and that's our guide. Ultimately, even compression, we cannot explain why it's so good compared to everything else. So, in some sense, you measure empirical success, but you try to make mathematically driven ideas to do this. So my favorite example, ever since I'm 13, is that there are things called black holes, right? And we are not supposed to know them because nothing comes out of it. But how the hell do you know it exists? It's because of Einstein's theory of gravity. If you knew the equations, you can actually predict it will happen. But it need not happen, but it's been verified much later. So this is like very much like that physics. You try to do something based on intuition, it'll work, but you won't be able to explain completely anything. Thank you. Is it clear? Thanks.
Yes, very
So,
clear.
I think we're on the top of the hour now. Milton, thank you for jumping on the call and participating with it. By the way, Milton is a friend of Fabio, so he knows how Fabio drives in Brazil. If Fabio's listening to this, don't say, because people like he knows how Fabio drives.
I talked to him.
Fabio drives very much like movie Burn. He drives like Burn Identity, right?
Fabio is just a
movie
little crazy.
Jason Bourne.
Jason Bourne.
Take care.
Exactly.
Good night. Nice meeting you, Milton. Thank you. Good night.
Thank you, Venki. Milton, as once, thank you very much for this opportunity to present to IEEE. Keep us posted. Let us know how this goes and how it works for you guys. We're available. Now we have this relationship. We talk, ask questions. I know there's a lot of questions for the
I love Sao Paulo. Don't bother.
And he loves Sao Paulo. Yeah, when we go, we look for an opportunity. Get us some visit out there. We'll go and visit and see how we basically can go and we'll participate and help you guys out. Okay. Have a wonderful weekend. Feliz Terceira. Abração para todo mundo.
Thank you very much, Marcello. Venki. Bye-bye.
Take care. Bye-bye.
Bye-bye.